All right. Thank you, everyone, for joining our talk here. So I'm Reza Farivar. At the moment, I'm with Capital One. This work was done when I was with Yahoo, when I have my Yahoo co-author, Kyle Nussbaum, sitting here. So yes, heads up, this is work mostly done in Yahoo, not Capital One, but hey. All right, so this is a rather more technical talk, probably, compared to some of the other talks you've been at the summit so far. We're talking about some benchmark that we wrote, and we're trying to figure out the performance differences between some of the leading streaming platforms. Now, streaming computations engines have become very popular, as most of you know from what you hear in this summit and lately. Of course, batch processing has been there for a long time, and everybody loved it, and Hadoop has been there for a long time, thanks to Hadoop. But new workloads are here, and everybody needs to handle streaming workloads, right? These platforms are designed to process continuous streams of data compared to batch processing models. They're designed to process data with low latency. Now, the low latency is very important, and it differs between what platform you choose. And a lot of people are working on getting the latency of their systems lower. You ideally don't want data to buffer, because as soon as you buffer, then you've lost your real-time properties of your systems. This is in contrast with batch processing models, where by design, data comes in, gets batched in, maybe 24 hours, maybe a whole week of worth of data, and then you run something for a long time. Here, you want to be real time. Now, a lot of these new platforms are designed to handle big data. Now, of course, the scale of big data differs from what, say, Hadoop can handle. But we're definitely interested in systems that aren't only running on one machine or two machines. We're interested in systems that run on clusters and can handle a lot of these. Right, so we had three interesting systems that we wanted to compare for ourselves, at least, to figure out which one of them worked better. We're talking about Apache Storm, which probably is one of the more mature ones among these platforms. Flink is another almost real processing system that is more of a newcomer. And then you have Spark with its Spark streaming model, which is not really real time. It's micro batch, but then there's a huge interest in it. And as most of you or some of you have tried it, and everybody's talking about Spark. So we wanted to see how these things compare with each other. So let's give a very quick background on each of these systems. We start with Apache Storm, right? The way it works is it allows the user to use what's called a topology builder API to build a graph, a directed acyclic, well, almost acyclic graph in this case, to create a directed graph that oh, the laser doesn't work. That's fine. That consists of basically, bolts and spouts. Spouts are where the data starts, enters into the system. Bolts are processing nodes that process them. And then the user connects the different bolts together with whatever topology they want, and data flows according to this topology. Now, graphs are not necessarily required to be acyclic, although most of the time it is usually acyclic. Now, in this case, for our purposes, we wanted to see what would happen if you have, for example, data coming in from Kafka, having a whole bunch of streaming processes applied to it, and their end results would go back to Kafka or to some database. Now, the second streaming system that we were interested in was Flink. Flink uses exposes an API to the user called Data Stream API that performs and allows the user to specify operations, sort of like map, filter, reduce, join, that sort of operation that everybody is familiar with in the world of Hadoop or Spark. So the same sort of API applies for Flink operations. Once you specify these operations, the system will turn these into a graph at job submission time. And the underlying graph then somehow ends up looking like what the user of Storm would have described. It also supports a Storm-compatible API. So again, in here, you have data gathering goes into Kafka. Flink does some processing with it. The results go back into Kafka or some sort of a database. For Spark streaming, now has an adaptation of the RDD model that they call DStream, the DStream API, which represents a microbatch, and you specify the duration of the microbatch. And then from that point on, you pretty much use them as if they were RDDs. So you can apply all sorts of map and reduce and join and all the nice things that Spark has to these streams. So from that point of view, you can think of the API being somehow similar to what Flink provides. Now, as I mentioned, the whole system is based on the micro batch idea, so small batch, process, move on, small batch, process. So again, Kafka, some processing happens in Spark, and databases or in Kafka. So we wanted to compare these platforms. Now, the issue was which benchmark would you choose? We wanted to pick up a benchmark that would compare the relative effectiveness of these systems in comparing how much throughput, which is events per second, they can handle, and how much latency they would introduce to the system. Now, latency here is defined by the time an event gets into the system minus the time the event is processed and goes out. We also wanted to compare these systems and make sure that how complete the answers are. In other words, we wanted to make sure that the computations are correct. Now, in general case, of course, the computations are correct. The problem comes in when you have an issue, a bad node, bad network connection, and then there's an error in the system. The question is, how does the platform handle that? When we looked at these, the benchmarks that were available, we didn't find anything very interesting. Most of the stuff out there were just very simple tests, figuring out the performance of a system in a speed of light test, which is basically get an event into the system, do nothing on it, get it out. Which, then different systems perform differently, but the question for us was, okay, this is not a real comparison. What happens when you really want to do stuff with data? So that's why we decided to go ahead and create an own benchmark, which mimics a real-world application that an enterprise would use. Now, in this case, the application that we are trying to mimic is a advertisement campaign counting. So we want to simulate if you had an advertisement system on a website and users come in and view pages and click on an ad and whatnot, and we want to count and see how many advertisement views we have. This benchmark that we created is available on GitHub, just in case it's open source. So our goal is to correlate latency with throughput in this benchmark. And we want to implement this advertisement campaign on all the 3 different platforms. We initiate some data, which is the number of simulated advertisement campaigns. For example, one company comes in and says, hey, I want to advertise such and such on my simulated website, and more of that. And then different number of ads per campaign are simulated. We store the initial data in Redis, basically the information about the different campaigns and which ad relates to which campaign are stored in Redis. Then in our benchmark, we have these things called producers. They basically are simulating users. The users would read the data and then start generating various events. They could generate view events, or click, or purchase, or things like that. And then events, once they're generated by some process that we wrote in Clojure, go into Kafka, and then from that point on, they're inserted into the advertisement processing campaign implemented in different platforms. So here is the basically view of the events, data flow of the benchmark. You have data, and I think I'm going to use the mouse to, I have animations here. So you have information stored in Kafka to begin with, right? The first thing that happens is that the event comes into the system and needs to be processed. The first step of processing is deserializing a JSON string, because a real user would probably create a JSON event, and we need to figure out, OK, what this JSON is. So the first processing step is deserializing the JSON string. Now, the next step after that is filter. So the event goes to the next step. We want to filter the events. Remember that the advertisement campaign could simulate different user events. It could be viewing an ad, or clicking on purchasing, or whatnot. In this case, we are only interested in events that are of type click. So we do a filter stage in this part of the application to filter out anything else. Now, after that, there's another step that we're simulating a real workload. It's basically projection. So what happens is that the JSON string or the event has a whole bunch of, typically has a whole bunch of different fields. When you write an application, you don't necessarily need all the fields. You need a basic set of them. And in this, the next step, the application would go and limit the number of fields, which is basically projection. Now, the fourth step would be to join. This is where you want to join based on the ad ID and campaign ID with some information that is already stored in an external Redis instance, so that when an ad ID comes in with an ad event, we can figure out which campaign ID this was related to and get back to our processing. So the process isn't only just processing. It also involves looking up something in an external database and comes back. So there's a join process here involved. After that, you have a time window aggregation, which in my next couple of slides, I'll also talk about that. This kind of involves in the mechanism used to figure out the latency of the system. So there's a little bit of windowing operations happening here. And finally, once we figure out the time that time window that an event belong to, we get to final steps of the application that adds the number of increase the number of events seen of this type, and then finally we write it down in Redis again for final consumption and figuring out the final latency. So one main question here is, how do we measure latency? And the way we handle this is that windows are periodically stored into Redis. So we create a timed window, and events come in and come into this window. The window's time duration could be arbitrary. And then, so in our case was 10 seconds. And then we define an SLA, service level agreement. And in our simulated case, we set our SLA to be 1 second. So we wanted to make sure all of the events are processed within 1 second and reported all the way down to the final database. So to handle this, the period of writes was chosen in a way to meet the SLA. For Storm and Spark, and we'll talk about this later, but for Storm and Flink, it was easy. For Spark, because of its micro-batch nature, it was rather hard, so we had to go around it. So we have a 10-second window, and events start to come in, right? What happens is that events get generated and then go into that window, and then for the next 10 seconds, tens of thousands of events come and get added to this window, right? Now, last event, of course, that belongs to this window is generated near the end of the time window. We have that timestamp, which is the last event in a window. And then later on, at some point, the results of this time window get processed by the streaming engine and is stored into Redis. And the time difference between the last event in a window and the time it gets stored in Redis, we consider this as latency. So, okay, I'm almost done with talking about general. Now I can get to talk about the methodology and then individual implementations. So in our test harness, basically, we give it a certain throughput. So for example, we tell it that, okay, create 50,000 events per second, or 160, 170,000 events per second. And then we measure the latency. There are 100 advertising campaigns in our run that you'll see the results later on, 10 advertisements per each campaign. As I mentioned, SLA was set for 1 second. This window duration was 10-second window. We used 5 Kafka nodes for our cluster, and to parallelize well, we used 5 topics. 1 Redis node turned out to be more than enough for our needs. We used 3 Zookeeper nodes, 10 worker nodes, and for each application. And there was a handful of nodes also used for masters and non-compute servers and whatnot. So the way we start is first we clear Kafka completely out of data. Then we populate Redis with the advertisement campaign IDs and ad IDs and those things so that we have that information ready. And then we launch the platform on individual, for example, Spark or Flink or Storm. We launch the application, and then we wait a little bit for each application to warm up, probably like 10 seconds or so. And then we start the producers, which simulate users, right? And then they start creating events at whatever given throughput that we have for that specific experiment. And then we let it run for 30 minutes just to make sure that we go past any sort of transient event that might happen in any of these systems. So we let it run for 30 minutes, and then by the end of the 30 minutes, we shut down the event producers and gather the data. Just for the hardware setup, we had homogeneous nodes. Each of the machines had 2 Intel Xeon processors with 16 hyper-threading cores. The nodes were decent enough, 24 gigabytes of memory for each machine. Machines were all on the same rack, and gigabit Ethernet switch connected them together. The whole cluster, in this case, our cluster has 40 nodes, which we use between 20 to 25 of the nodes in each run. And as I mentioned, different instances of producers put events in Kafka. Turns out what each machine could at most create up to 17 for our case, 17,000 events per second. So we had like up to 10 machines in parallel simulating user events and pumping into Kafka. Now, one question is, why would we go and pick like 10 workers in different experiments, right? Whether Spark streaming or Flink or Storm, why would we use only 10 workers? Of course, typical deployments of Storm clusters or like Spark streaming clusters might have bigger node, but a lot of times, at least in our use cases, they're multi-tenant, and a typical application, Storm application or Spark streaming application, usually works with 10s or 20 or so, nodes. So that's why we chose this number. So now let's talk a little bit about the different implementations that we had. For Flink, we tested on the version 0.10.1 snapshot, and we wrote the application in the Java API, the data stream API. The checkpointing feature was disabled for Flink, so that if there was, so the checkpointing feature is the way Flink ensures at least once processing and of course adds more overhead. We had it turned off. For Apache Spark, we tested on 1.5. By now it's 1.6 point something. The application was written in Scala using the dstream API. We didn't do anything particular to get at least once processing. And for Apache Storm, we tested on both 0.10 and 0.11 snapshots. I'll tell you later why. We used the Java API to write the application. And for 0.10, we had hacking turned on. For 0.11, we had hacking turned off. So let's look at the results for Flink. To decipher this graph, you can look at it. This is a percentile comparison graph. So the horizontal axis shows the percentile of tuples completed. The vertical axis is showing the time, like basically latency after the window was closed, right? So for Flink, you can see that it's very linear. And remember, we are targeting 1 second SLA. So we want most of our events, or all of our events ideally, to be handled within 1 second of the time they come in, right? So as you can see, for the people who are back there, I'm trying to see if I can use my mouse. So the first thing here, for example, is 2,000 milliseconds, right? So 2 seconds is here. We want everything to be handled by 1 second. And in this case, we see that the majority of the tuples, up to 90% percentile, are in fact handled within the 1 second service level agreement, right? Also, the very linear nature of the graph shows that the latency induced is actually much lower than 1 second. You don't want to say Flink has 1 second latency. Well, what we are showing here is that actually up to 99% of the tuples are handled within the 1 second SLA that we want. Now, there is a sharp curve toward the end that indicates that a very small percent of, less than 1%, of tuples that are not handled within 1 second SLA that we are asking the system for. Now, of those late tuples, most of them are actually written within a few milliseconds after the 1 second. So that's fine. But some of them sometimes actually go up, especially, and this is, of course, happens only under extreme workload cases. When the workload number, which is the throughput number that we're showing on that slide with the different colors, when the throughput is small, system handles everything. When you increase the throughput, of course, is when the system gets under pressure that some of the tuples go past the SLA. Now, beyond 170,000 events per second, that throughput, that was when we started to see Flink falling behind. And I have a picture of, I have a graph of system falling behind later on. Actually, that's for Spark streaming, but any system would actually behave like that. So I'll show you that in a couple coming slides. So let's talk about Spark streaming. The Spark streaming benchmark was written in Scala, as I said, using dstream. And for the Kafka consumer, we use the direct Kafka consumer. There's, of course, other Kafka consumers in Spark. We use the direct Kafka consumer. It's micro-batching, and this is different from the pure streaming model, right? Now, to meet the 1 second so the way actually we designed this benchmark is read 1 second's worth of data and then process them, right? So that at the end of it, then we write the data down to database. And we're hoping that by setting the micro-batch duration to 1 second, we can handle the 1 second SLA. Now, this is, of course, the theory for higher throughputs. The 1 second micro-batch is just simply not enough. And I have a slide on that, so I won't go too much into it. But then we had to increase the micro-batch duration to be able to handle the throughput. And as a result, we were missing the SLAs by as much as we would increase the micro-batch duration. Now, joining the data with Redis is also a special case because the way the Spark works, you can't actually just go and make a new connection to Redis. So again, we had to jump through some hoops to make sure that we make one connection to Redis and make it consistent, and then just use that in one micro-batch after another micro-batch. Now, Spark was interesting because, and I'll show you the results in the next slide. But Spark actually took us a longer time to implement and get good results out of. Because unlike the previous systems where your only tuning knob is the number of machines that you're throwing at it, here you have two dimensions to tune. And as a result, you can imagine there's a two-dimensional space that you have to traverse to get the best results. So one of the parameters is micro-batch duration. The more data that you batch, the less overhead you will have for starting a micro-batch and then finishing a micro-batch, right? And this variable is just not available in a pure streaming system. And then the second one is kind of similar to what a pure streaming system has, is parallelism. So how many machines do you want for each stage of the computation? Now, again, this is kind of similar, but not quite similar, because you can imagine in a pure streaming system, an event comes to a stage, and you want to say, OK, up until this stage, I had 5 machines here. The next step, I want to have 25. OK, a simple algorithm. When I want to route it, I now route it instead of to 1 of 5, I'll route it to 1 of 25, right? But due to the micro-batch nature of Spark streaming, now you have a whole number of data. And if you want to change the parallelism level, now you have to go through a reshuffle algorithm, which itself is time-consuming. So that's why coming up with a tuned solution in Spark streaming was much harder than what we could achieve with Storm or Flink. Now, if you set the micro-batch duration sufficiently large, in this case, we've set it to 10 seconds micro-batch. Remember that we are hoping for 1 second SLA, so 10 seconds is like really bad. But if you set it to 10 seconds, it can handle pretty much everything within half time. So this is an average, right? So this is showing like everything is handled within 5 seconds. The window is 10 seconds. Everything is handled within 5 seconds, except maybe a couple events that arrive right at the edge, and they get handled at the second batch, right? But this is not the best Spark streaming can do. And to get better than this, what you have to do is reduce the time required for a micro-batch. Now, if you reduce it little by little by little, you get into some interesting operating domain where almost 20–25% of the events that come in are handled in the first microbatch. The next 25% handled in the next one, the third one, the fourth one, which is interesting. And when I show you the next slide, this kind of makes even more sense. So the system in this case is on the verge of falling behind, but it's not quite falling behind. But this is the best that Spark could do. So for example, in this case, I think the window was set to 4 seconds. And then, of course, if you get the window small enough, in this case, 2 seconds, then the overhead of starting a Spark microbatch and stopping a Spark microbatch, and of course, there are other overheads involved, including getting all the data, because all the data across the Spark cluster to the head node for statistics, because every time a Spark job, whether it be a job or a microbatch, finishes, all the data has to come back to the head node, which again introduces a whole bunch of overhead. So in this case, when we set the duration too small, you see that the system just falls behind. And by the way, this is the same graph that you would see of any other streaming system, Storm or Flink, if you cannot just cope with the throughput. I have 7 minutes left. Right, so as I mentioned, tuning the batch size was time consuming, and it was actually, we had to run this for a whole number of days to figure out. One interesting thing that I want to add here was that at the time, Spark recently just added a feature called Backpressure that was at least an attempt to help the users with getting the micro batch duration correctly. So at least the goal is to set it, let the micro batch duration large enough, and the backpressure feature will try to reduce it, but it didn't work for us. Actually, it made everything worse. So now finally, let's come to Storm. Storm actually behaved very similarly to Flink, which, to be honest, is not a big surprise because both of them are real streaming systems. One interesting thing for us was it behaved kind of nicely towards the end. Storm could handle traffic up to 130,000 events per second with hacking enabled. Now, when you have with hacking enabled, you also get at least once processing. After 130,000, the system would actually fall on its face. So that was in Storm 0.10. In Storm 0.11, there was a feature added that you could turn off hacking. It still wouldn't provide you at least once, but at least you could run your topologies without getting into some fundamental issues. So with 0.11, we also ran with hacking disabled, and then we could easily handle everything up to 170,000. We didn't run more than that because none of the other systems actually could handle that. And behavior of Storm's late tuples are pretty much similar to, again, Flink's late tuples. So that means that most of the majority, 99 percentile or 90 percentile of the events, depending on how much throughput we put on it, are handled within the 1 second SLA. The only interesting thing that we saw was that the tuples that were late in Storm was just slightly less late than what Flink could do. So, three-way comparison. I just want to put the behavior of different systems at their best performance, so that you can see that Spark streaming cannot actually touch the sort of SLA times, latency times that the other two systems are providing. You can see that Storm is doing a little bit better than Flink, but they're kind of similar in performance. And if I want to, this graph is different. On the horizontal axis, I have different throughput rates. And on the vertical axis, we have the 99th percentile time. right? So if, for example, I'm looking at this point, this means that for this throughput 130,000, the 99 percentile of Spark streaming events were handled within 6 seconds, while at the same, the other two systems were handling them less than 2 seconds. One, like for example, the red one, which is Storm without ACK, could handle everything in definitely less than 1 second, while some other systems, was more than 1.5 or so. All right, so to talk about some of the future work, basically, there are many variables involved here, and to be honest, we didn't even try to adjust all of them. The applications that we wrote were rather simple. We didn't try to pull any Herculean effort to really, really optimize each of these algorithms. We tried to write some simple enough algorithms that a decent enough programmer would write within a day or two. Two words of caveat is that the SLA deadline of 1 second in real world use cases is rather low. And we wanted to test the limits. That's why we actually chose 1 second. In a lot of real world systems, 10 seconds is good enough, right? And that actually helps a system like Spark streaming a lot, because when you're working in the 1 second, 2 second sort of duration, the overhead of job starting and finishing and thing is huge, comparatively huge. Actually, I think the lowest that we could get the Spark streaming job was 300 milliseconds. Anything lower than 300 milliseconds, nothing would work, basically, at no throughput. The other thing is the throughputs that we tested are rather high. Again, 170,000 events per second is really, if any company has that many events coming in, this is their last problem. We didn't test with the exactly once semantics. That's probably for future work. It would be interesting to see if you turn on the checkpointing on Flink and completely with hacking and everything, and try that maybe in Storm, how they perform. We didn't try that. And we didn't quite check the correctness at large scale. We do check for correctness of results, but not when you increase the when you run the benchmark at scale. We didn't check it. We just checked it for like very small values. And basically, to conclude, the competition is actually very interesting at the moment. Ever since we did that, back then nobody knew about NiFi. Now everybody's talking about NiFi, so it would be interesting to see how that gets in. And then there's, of course, other guys. SAMSA would be interesting to test and whatnot. And the other conclusion is each of these platforms have their advantages and disadvantages. Like, for example, you could see that Spark streaming has higher latency. But then again, Spark itself, the ecosystem, does so many things that you have the advantage of familiarity of your developers with the Spark SQL and machine learning and everything else. So, there's that. If you want really, really good latency, go for Storm. Other important factors is whether security is, for example, integrated into your tools or not. Like, for example, Storm has a really good mature set of security features added in. Some other platforms don't. And each of these have active communities. So I think it's going to be interesting to see what happens in the future. All right, that's about it. Thank you.